So how do we run this on an EC2 instance? Well, you have to select the instance first. In this case, in this example, we're going to just download the lit llama model, which has around 7 billion parameters. We need a GPU that can hold that model. And there are different instances, like a P3 is very popular one. But in this case, we want more GPU memory. We use a G5 instead. And then it's a matter of just doing the basics, like install the CUDA drivers. And for that, you have to allow the CUDA repository and then just install the drivers. In order to check that you install the drivers correctly, you can simply run a torch command that tells you whether the CUDA driver is available or not. And this should return true when you run it. Obviously, for that, you first install pip and then install PyTorch. And then you run this one-liner, and it tells you that the driver was successfully installed. You might have to reboot the machine in the middle of this because this kernel change. To install the Llama model itself, which is a kind of open at the moment, you just clone the repository. You install LFS, which is the large files for Git, and you clone from Hugging Face the model. This is a checkpoint for 7 billion parameters. And then we need to convert those weights into something that can be used by this model. And there's a Python command for that. This is just straight out of the documentation. There's nothing secret from this. I'm just putting the commands in one place. So if you want to do it, you can go ahead and do it yourself. And then just test that it works. Basically, you run the generate.py command, and this command will run the model with the prompt. The code on the lit llama is based on NanoGPT. So it's based on the same code base that the code I showed you was based. So you should be able, if you follow this tutorial, you should be able to read that code and understand it very easily. So this is a very similar code that is used for the Llama project. And we'll talk a little bit about that in the few slides. So going back to the transformer, it has two stacks on it. And usually people say, okay, this is the encoder stack, and this is the decoder. You're going to see this in the literature a lot, where they talk about the encoder and decoder stacks of the transformer. And there are many models that are only using one side. For instance, our model, that the one we built, is only the decoder side of the transformer architecture, since we are not doing translation. The original code was used for translation, and we are only trying to do language model, which is predicting the next token in the sentence. So there are models which are only the encoder side, there are models which are the decoder side, and there are models which use both sides of the transformer. So in an example of translation, how do you actually use these two stacks? You have two inputs. So what exactly are you feeding here and here? So I wanted to clarify that. And how exactly do you get the output here? So we'll start with the toy sentence. The way that you use this, you put the input in the encoding side. And then what you do is you initialize the output of the decoder side by only using one token. And usually this is a beginning of sentence token. And this is a special token that you usually add to your vocabulary. Then what happens is that you run the model and you have one output. And this is the output here, the word, the first word that is predicted. And obviously you put that word back into the decoder side and you run it again. And with that output there, and you have another word here, and you put that back into the input, you put the input back, and so on. And you keep iterating and completing the output. So this will be one word at a time, be predicting what would be the translation. And you stop when you have either the end of sentence or some kind of number of items, number of tokens that were predicted. If you look into that model and you pay attention to this part, we have an input here. And this is the information that is being transmitted from the encoder to the decoder. So in essence, this has the knowledge of what the meaning of this sentence is. And then it gives that knowledge to the decoder to translate it. In essence, this has all the information of the input sentence, and it has all the meaning of the input sentence. So all the information that you should have in order to be able to translate this is somehow in this vector. This is called contextual embedding because it's not only an embedding, but it also has the full context of the meaning of the sentence in some way. We are going to touch on this a little bit more in the next session, but people said, okay, how about I feed here a full document with, with a lot of text, and then I feed another one, right? Let's assume that the of this sentence here, the prompt here, is instead of being 4 or 5 words, it's around 16K or 32K. So these are long prompts. What if I feed chunks of documents here? What? Well, this part here should have the context and the meaning embedded into it. So what's happening is that somehow all this document is being summarized in this vector. And we could use that as information. And this is how people started to design what is known as vector databases. So basically, you put all these documents, you run them through the model, and you say, okay, if these documents are similar or have similar meaning, these embedding vectors should be similar. So if we do a matching of those embedding vectors in a database, and we say, give me the most similar vector to this document, I'm going to be able to find the documents that were similar to this, regardless of whether the wording is different. If the meaning is similar, I should be able to find them. So this opens the whole thing about using this model for search, or using these models for, trying to scan through a set of documents. You just index them using these context embeddings, put them in a vector database, and then try to do the closest match by using some similarity metrics. In our little example, this was, 1, 2, 3, 4, 5, 6 words, which were 6 tokens. The models that are being developed now, they have 32,000 words of input. So basically the prompt can be 32,000 tokens, which you can write, a couple of pages of text. You could have a full book divided into pages or paragraphs, and then feed those to the model and get those contextual embeddings. The input size is fixed, but it's long enough. I have a long sentence, and then I finish that before the 16K. I finish with a token which is called end of sentence. And, as long as this is less than the maximum prompt size, you're good. The problem is when you want to put more than that. And in that case, you can do, well, you can say, well, instead of the whole book, I can feed only the relevant parts. But how do I feed the relevant parts? Well, I need to be able to search for them. And how do I search for them? Well, you can use an LLM to search for it by using these contextual embeddings and putting them in a vector database. Using the LLM to find the relevant data, then you grab that relevant data, you put it back in the LLM, and then you get the output, which is more specific to what you were asking. We should talk a little bit about the training and fine tuning. But imagine that you have a trained LLM, you train it to, in a large corpus of data, and you ask the LLM, create a Python function to generate the Fibonacci sequence. No? And you pass it through the LLM and you get the answer. And the answer is create a Python function to add 2 numbers. So this is not what you were looking for. the M was trained in a large corpus of data, and maybe some of those were sets of questions about Python programming. And when you feed one question, instead of giving you the answer to that question, it gives you another question because it learns that after one question, there's another question in the test. So this is clearly not what you intended to do. But according to the model, the prediction was great because it predicted something that was likely to happen. So the problem is that we have to tell the model in some way that when we ask something, the model should give us an answer to that. And the model has no clue at the moment how to do that. It was only trained as a language model. So how do we do that? And this is the part where the reinforcement learning comes in. So reinforcement learning is a vast field, and I will not pretend to be an expert on that. But there were a couple of papers, and you will notice that both of them are from OpenAI. One is the PPO paper, which is the proximal policy optimization. This is an algorithm to models using feedback, and specifically human feedback. So this algorithm PPO is one of the core algorithms that is used to train these models to learn to follow instructions. The paper that shows how this was done is this one called Learning to Summarize from Human Feedback, where they grabbed a lot of data from different posts. Particularly, they used the TLDR dataset, which is a set of posts from Reddit where people summarize what the post means. So they can grab the whole post, they can grab the summary, the TLDR, and then use that for training the model. Once they do this reinforcement learning, the model learns to answer these kind of questions or commands instead of trying to predict the next question or something like that. So this is in one of the papers, and it's also in one of the OpenAI in the OpenAI's website. But basically, the idea is that they grab a lot of Reddit posts and they give them to people, and people say, okay, this one is better than the other one. So they sample from there, and people are categorizing them. Then they a reward model, and then they use that reward model to train the language model. This is called sometimes training, whereas the previous part that we did, which is learning the language, is called sometimes pre-training. This is very confusing because some other people call this part of the language, they call it training, whereas they call the other part, which is the reinforcement learning, they call it the fine-tuning. So sometimes this nomenclature can be a little bit confusing. But basically, what is happening as a big picture is you have a model that is only able to predict, but that model can blindly predict tokens. You have to teach the model, okay, you know how to predict tokens. You also need to train the model to answer or follow directions. And this is done using this reinforcement learning, using this algorithm called PPO. And the other part that people often talk about is fine-tuning. And again, the nomenclature here is a little bit confusing sometimes, which is when you want to grab a model that was properly pre-trained and trained, and you want to train it specifically for some very specific tasks. For instance, you want to grab one of these language models and train them specifically for, I don't know, cancer biology papers, something like that. The problem with that is that you have a very large model usually, and in this case, you need to train the whole model with this new data set that you have, this specific data set. But if the model is large, then the problem is that fine-tuning requires a lot of resources. So people have been thinking about how to optimize this, and there are several tricks that you can do. This is particularly done a lot in imaging side, where you do you pre-train model and you fine-tune it using only some of the layers. So instead of using all the layers in the model, you fine-tune only the last few layers. There's another approach which is also generic, not only for language models, but for all kind of models. And a very popular one is called LORA. LORA is a low rank adaptation. It's used mainly for language models, but it's generic. You can use it in imaging models as well. And the idea is actually quite simple. What they do is, if you have a matrix of weights that you train with the models, what you can do is to keep this completely frozen, so you don't train on this, but you add two matrices here. And these two matrices, instead of being full matrices, they are small. What you could get is that you are training a lot less parameters. That fine-tuning step is not affecting the weights of the original model at all. And it is actually only changing a very small part of it, so it's much faster. One of the core concepts where that this is building on is that when you are adapting to a specific task, it's been shown that the pre-trained models have a low intrinsic dimension. So this means that if you're fine-tuning a model to a specific task, then you're not changing all the weights in the weight matrices. You're just changing only a subset of that. And here they give an example. Let's say you have a matrix W0 and you add a delta W matrix, and this could be what you are adapting. So this could be the fine-tuning, whereas this one would be the original that you freeze. And so instead of doing delta W, you use two matrices which are of lower rank. What does this means is that now if we go a little bit into the equation here, so the delta W is this matrix, but instead of being a full rank matrix, instead of having all numbers filled there, you have a very thin matrix which has only a few rows here. This part is usually called R here, and another matrix which also doesn't have too many rows. Again, the same parameter R. When you multiply these two matrices, you will get a full matrix like this, but the rank, the dimensionality of the matrix is much smaller. And obviously the number of parameters that you have here and here is much smaller than the ones that you could have if you were training a full matrix like this directly. So what happens is that if you use a small r, and in the paper they use 4 and 8, and they even use an R of 1. So this is just a vector, a single vector for adapting. So if you do that, you have a much faster fine-tuning of the model. And in many cases, what you can do is you can train, a 7 billion parameter model in a couple of hours, which is a lot faster than what it would take you to do if you were retraining the full the model. The LoRa adaptations are, like I mentioned before, they're widely used. They're used not only for language models. These, the condition that they say, well, just put an R that is much smaller than the dimensionality of the model. And here they show that for a GPT-3 with 175 billion parameters, they reduce the memory consumption from 1.2 terabytes to 350 gigabytes. With R equals 4, they say they reduce 10,000 times from 350 gigabytes to 35 megabytes. So a much smaller. And what they show in the paper is that even though you're using a much smaller dimensionality in the adaptation, this still has the ability to adapt to learn your specific dataset. Now, one thing that you can see here is that you have this that was frozen. You load the original model, you do the low rank adaptation. So for each W matrix that you have, you do a low rank adaptation, and you don't need it to do it for all of them. You just do it for some of them. You know, the paper mentions if you do it here and here, it gives us more benefit, where if you do it here and here, it's not so beneficial, and so on. They do a lot of comparisons, so you can go and read those. And then what you have is a set of frozen weights and a set of specific weights. So you save this into a file, and let's say you train this with, you know, cancer biology papers. And then what you could do is when you need to use the model, you load those, you load the frozen ones, you load the original ones, and you load these adaptations, you add them together, and you have a model which is able to respond to that. Okay. But another thing you can do is you do another adaptation. And this other adaptation, instead of cancer biology, is, I don't know, Python code. Or you do another adaptation, which is Java code. And you do another adaptation, which is C code. And you do another adaptation, and you get you can swap in and out these adaptations because they're very cheap. And the original model didn't change. So these are frozen in an original file. And then you can swap in and out these weights, which are much smaller. They are claiming that, you know, this is like a 30 something here megabytes of weights. And you have an adapted model that can do fine tune on some specific task. You have one model with many adaptations, and you swap them in and out, and it's very easy and cheap to do that. And you can even do it on the fly. Now I have a request for Python, for Java, for C, and you swap in and out the adaptations as needed. This is a generic method. The good thing is that it's flexible. It allows you to swap things on the fly, and it's very cheap computationally to fine tune compared to doing the full fine tune. We often see, and again, this is a little bit weird nomenclature, but when we talk about pre-training, we're talking about learning the language. When we set training in some cases, or instruct, the model is called dash instruct, then it learn to answer questions and follow direction. This is reinforcement learning or PPO algorithm. Sometimes when we talk about fine tuning, we are talking about training to learn a specific domain. Now, there are other people which usually call fine tuning the instruct models. So this is very confusing. And then adaptation, you're going to see this. There's another adaptation mechanism that is very common that is called a perf. You're going to see that as well. LORA and perf are two different flavors of doing something similar, and you will find it. I mean, they're not exactly the same, but they are mechanisms for adaptation. So I wanted to talk the generative pre-trained transformers, and these are called GPTs. So in the case of a GPT, what you see encoder stack only. So basically the encoder stack is gone, and you're using the model to train for language. And that's usually the diagram that you will see. These models tend to be large. So what are the scales of the you often see? And obviously, this part of the conversation will not age very well. If you're looking at this recording in distant future, like instead of Tuesday, you're looking at it on Wednesday, then all this probably is going to be obsolete. So the history started with GPT-1, and this was the number of parameters that were in GPT-1, 100 million parameters. This is something that you can actually do yourself with a bunch of GPUs. One of the models that will, the code that I put there for the training, it trains on only one GPU, and it has a similar number of parameters. So it's not a huge challenge. Now, they did train it for a month or so in 8 GPUs because they trained on a much larger data set, obviously. But then things started to scale. We see 1.5 billion parameters, 175 billion parameters, and for GPT-3. And when you get to GPT-4, they were kind of undisclosed, but we're going to see that actually the details leaked out last week. So we roughly know what they claim to say. They say that training GPT-3 costs around $5 million. So these models are becoming very expensive to train. On the Google side, we have a model called Palm. And again, this is the number of parameters, the progression of, they say 540 billion parameters. These are trained on 4,000 TPUs. TPUs are tensor processing units instead of a GPU, which is a graphics unit that used for matrix multiplication. They created their own chips that are specifically designed for tensor multiplications. And this is the version 3 of the chip, so it's the latest that they have. And they say they use 4,000 of them during I don't know how long. So these models are getting bigger and bigger. And why are they getting so big? It's because there's something that happens with neural networks in general, that as you start more and more parameters, more neurons to it, the models start to get some emerging behaviors that were not obvious. You know, if you grab one logistic regression unit, it's not obvious that you're going to get an image recognition system or a language model when you aggregate a lot of them, right? And so as you start to add more parameters and you train with more data, you start seeing emergent behaviors. And this is, I think, a chart from Google, where they say, well, as we scale the number of parameters, we start to do things that we were not able to do with less parameters. And they start from language understanding to translation to common sense reason to logical inference and so on. And this is the key reason why these models are getting big. Well, big by today's standards, and difficult and trained. The GPT-4 model, they say that they use 1.8 trillion parameters spread across 120 layers, mixture of experts, which means that they train different networks, so 16 different models with roughly 110 billion parameters each. And they were trained on a data set of 13 billion tokens with a context length that is the prompt size of 32K. If you remember, when we did our training loop, we had a batch size of 32 or 64. Their batch size is 16 millions. So these are large numbers. Obviously, they need a lot of hardware to do that. They say that they put 25,000 NVIDIA A1 GPUs for training, and they report that it took around 100 days. So if you do the math on how much, if you go and buy those in Amazon, this would cost around $63 million to train a model like this. But obviously, how many times did you create a complex program from scratch and you run it and there's no syntax problems and it runs exactly as you expected? Well, that doesn't happen often. So the same with the models, right? I mean, such a complex model, you have to train it several times. There are things going wrong here and there. The quote is that it costed them more than $100 million to train it. This is from one of the leads at OpenAI. Obviously, we don't have budget to train one of these for ourselves. This is very costly, but we could have some open LLM. Until last week, one of the models of choice was Llama. It's a large language model from Meta AI. There's an open version of this code from Llama, which is again based on Nano GPT, which is the code that we coded as well. Obviously, you need the framework, which is the code to run, you need data set, and you need the model weights. And these all three were made open source by different people. The data set is called Red Pyjama. And in case you're wondering why, there's a kid's book that is called Llama Red Pyjama. And then there's the open Llama weights that you could download. And this is the example that I did in the EC2 instance. So if you want to run it yourself, you can just spin an EC2 instance and run it yourself there. And exactly 1 week ago, Llama 2 was officially released by Meta as an open source. Now you don't have to do this anymore. You can just run Llama 2 directly, which is a new version trained with more data. And they have different flavors of it as well. They have 7 billion and 70 billion parameters. So this goes up to 70 billion. And you can run them as well. But if you want to see which models are the best so far, you can go to the Hugging Face leaderboard, the OpenLLM leaderboard, and it tells you with different metrics which models are best. The best one is a retrained version of the Llama 2 model. This was with the Orca dataset, And since it's an Orca data set, they call it Free Willy. And this was released by Stability AI. So if you go now at this moment, or at least yesterday, to this leaderboard, that would be the best model, that top model in there. But I'm sure this tomorrow will change. So really, this is just to give you an overview of what's out there and how you can use it. These are the details of the Llama 2 models. And again, you can Google it and you can download it and use it. That's all I have for today.